Imagine you are managing a 100 petabyte Weka storage cluster.
Oh, that's quite the setup.
Right. It is the absolute backbone of your organization. It's processing these massive artificial intelligence training models at, millions of input and output operations per second.
Just humming along.
Exactly. Everything is humming. But then suddenly the application team starts screaming.
They always do.
Yeah, they do. The AI training pipeline has just ground to a total halt. Throughput has dropped by half. But you look at your standard network, monitors your switch telemetry, your server CPU graphs, and everything is perfectly green.
Which is terrifying.
It really is. You are basically flying blind at Mach 3. And your multi-million-dollar hardware investment suddenly feels like this black box that you just can't crack open.
That is the ultimate nightmare scenario for literally any storage architect or systems engineer. I mean, when you are dealing with parallel file systems operating at that extreme scale, standard operating system metrics are, well, they're functionally useless.
Because they just don't see deep enough?
Right. The network might be up, the CPUs might have capacity, but the actual storage fabric itself could be heavily degraded. And you honestly wouldn't know until the application layer just catastrophically fails.
So today, we are going to decode the exact telemetry pipeline you need to prevent that exact scenario. We are executing a deep dive into 2 highly technical integration guides from Supermicro.
Specifically, we're looking at their release 3.12.0 documentation from June 2026, right?
That's the one. These guides detail the precise nuts and bolts architecture required to bridge Weka high-performance storage environments, and that covers both the 4.x and 5.x generations with Supermicro's SuperCloud Composer.
Or SCC, as we'll probably call it.
Yeah, SCC.
The underlying goal of these source documents is basically to map out a central nervous system for your storage infrastructure. We aren't just looking at how to make 2 proprietary systems shake hands here. We are really dissecting an entire observability philosophy.
Okay, let's unpack this because when you first open these manuals, you might assume you just give the SCC appliance an IP address for the Weka cluster, supply some credentials, and just call it a day.
That would be nice.
It would be. But the architecture here is deliberately indirect. It is a multi-stage telemetry pipeline.
Yeah, a direct connection simply doesn't scale in modern enterprise architecture. I mean, the pipeline detailed in these guides flows from the Weka cluster over to a dedicated Weka exporter, then into a Prometheus database, and finally up to the SuperCloud Composer dashboard.
It's a journey. But before we talk about that pipeline, we really need to understand the beast that's generating all this data. Let's talk about Weka itself, because this isn't, a standard network-attached storage array.
Not at all.
This is a massively parallel file system built for NVMe flash and InfiniBand networking.
Yeah, Weka fundamentally bypasses the traditional Linux kernel storage stack entirely.
Which is wild to think about.
It is. In a standard setup, when an application wants to read a file, the request has to travel through the kernel, right? Which inherently adds latency. But Weka uses its own custom drivers to talk directly to the NVMe drives across multiple physical servers simultaneously.
It just scatters the data and the metadata across dozens or hundreds of nodes.
Exactly. So returning to your initial scenario, monitoring that environment is it's like trying to monitor a high-frequency trading floor in real time.
Oh, that's a good way to put it.
Yeah, millions of microtransactions are happening across hundreds of desks simultaneously. Nanoseconds dictate success or failure. So the Weka exporter, in this analogy, is essentially a specialized audit algorithm that's deployed right onto that trading floor.
That is an incredibly apt comparison. The exporter is this lightweight containerized application, and it knows how to speak Weka's proprietary internal API. It's constantly polling the cluster, checking disk health, InfiniBand port status, latency metrics.
Taking all that chaotic proprietary data and translating it.
Right, translating it into a standardized HTTP endpoint, specifically operating on port 8001.
But there is a catch. The exporter doesn't actually have a memory.
Ah, right.
It only knows what the trading floor looks like at this exact millisecond. So if the application team asks what happened an hour ago during, say, a latency spike, the exporter is useless.
It has no historical context, which forces us to introduce a time series database. And that is exactly where Prometheus enters the architecture.
Oh, yeah.
If the exporter is the local audit algorithm on the trading floor, Prometheus is like the Securities and Exchange Commission's permanent time series audit tape.
I like that.
It operates on a pull model, reaching out to the exporter every 60 seconds or so, grabbing that snapshot of data, and indexing it against a hyper-precise timestamp.
And that separation of concerns is really the brilliant part of this blueprint. Supermicro didn't try to build a custom Weka polling engine inside SCC.
That would have been a nightmare to maintain.
Exactly. Instead, they built SCC to natively query Prometheus using POMQL, which is the Prometheus query language.
Meaning SCC is totally vendor agnostic at the monitoring layer. It doesn't need to know how a Weka cluster works or how a Cisco switch works or how a Linux kernel works, right?
Right. It just needs to know how to ask Prometheus for a metric and render it on a screen. The complexity of the storage hardware is entirely abstracted away from the visualization layer.
So elegant. So this brings us to the actual implementation. The 4.x.x guide gives us a look at the earlier, more monolithic approach to deploying this pipeline.
They refer to it as the minimal Weka monitoring setup, I believe.
Yeah, that's the term. It assumes you have a dedicated Linux host sitting completely outside the storage cluster, acting as your monitoring server.
And the guide starts with security, specifically generating the Weka auth token. The command provided is Weka user add Wekamon cluster admin.
Okay, I have to throw a flag on this play right here.
I had a feeling you would.
I mean, assigning the cluster admin role to a monitoring script, that breaks every principle of least privilege I can even think of. Why does a basic metric scraper need the literal keys to the entire kingdom?
It is a totally valid concern, and it really highlights a friction point in hardware-level observability. See, a read-only user in Weka can tell you if a file system is mounted or, how much space is left.
The basics.
Right, the basics. But a read-only user cannot query the deepest layers of the hardware fabric.
You mean things like the firmware state of the NVM drives or the error counters on the InfiniBand host channel adapters?
Precisely. To get that microsecond-level telemetry required to genuinely monitor Weka's performance, the exporter has to invoke API calls that interact with the bare metal. And in the Weka permission model, those specific calls are gated behind the cluster admin role.
So it's a trade-off.
It is a calculated architectural risk. You trade strict least privilege for total comprehensive observability.
Which I guess explains the extreme lockdown procedure that follows in the manual. The guide dictates moving the generated JSON token, the Wekamon auth token.json file, to the monitoring host and immediately running sudo chmod 400 on it.
Locking it down to root-only read access.
Right. I understand restricting file permissions, but mechanically, how does this actually play out? If we lock this file down so only the root user can read it, how does the exporter container, which presumably shouldn't be running as root, actually read the token?
That gets into the underlying mechanics of the Docker daemon itself. In this 4.x era setup, the guide uses Docker Compose.
Okay.
When the Docker daemon, which does run as root, mounts that specific JSON file from the host file system into the container's virtual file system, it handles the file descriptor pass-through.
Oh, interesting.
Yeah, so the containerized process can read the contents of the mounted token without actually needing to change the underlying host permissions.
So it basically creates a secure envelope. If a bad actor compromises the monitoring host through some other vector, say, like a vulnerability in a different web service, they would just drop into a low-privileged shell.
Exactly.
And when they try to read that Weka token to pivot into the storage cluster, the OS just blocks them.
The token is secure, yes. But the deployment methodology itself in this 4.x guide is what I actually find problematic for modern enterprise environments.
Tell me about it. Let's examine the docker-compose.eml file they provide.
It's quite something.
I'm looking at it right now. It spins up the Weka Solutions Sexport image and the Prometheus image. It seems incredibly straightforward, almost, dangerously simple. You just drop a YAML file in a directory and run Docker Compose up.
Well, the danger isn't necessarily in the simplicity, it's in the networking configuration they mandate. The guide explicitly instructs you to use network mode host for both of those containers.
Oof, yeah. For those listening who might be unfamiliar with the depth of the Linux kernel network stack, network mode, host completely bypasses Docker's internal virtual bridge network.
Completely.
The container doesn't get its own isolated IP address at all.
No. It binds directly to the physical host's network interfaces. So if the Prometheus container is configured to listen on port 9090, it just outright claims port 9090 on the physical server's ethersudo interface.
So if you have an enterprise environment where the monitoring team decides, hey, they want to run a second instance of Prometheus on that same machine to scrape a different cluster.
It's an immediate fatal collision.
Right. The second container will just crash on startup with a port already in use error.
And beyond that, you are creating a very rigid, monolithic failure domain. You are tying the lifecycle, the networking, and the fate of your critical telemetry pipeline to one single operating system.
Meaning, if that specific server needs a kernel patch and requires a reboot.
You lose all visibility into your storage cluster for the entire duration of that maintenance window. You are flying blind again.
That rigidity is exactly why the industry largely abandoned single-host Docker-composed setups for mission-critical infrastructure years ago. We needed systems that could self-heal, self-route, and actually survive a host failure.
Which bridges us perfectly to the second guide we are analyzing today, the Weka 5.x.x integration, focusing specifically on Weka version 5.1.24.
Yes. This guide just abandons the static Docker host entirely and moves the telemetry pipeline directly into Kubernetes. We are shifting from a monolithic paradigm to a fully orchestrated dynamic paradigm.
To really ground this in reality, let's map out the exact environment the Supermicro Guide uses for this Kubernetes deployment.
Good idea. Set the scene.
You have the SEC appliance sitting at IP 172.31.44.116. You have a massive Weka cluster composed of 6 physical nodes, and they are sequentially named S1 through S6, operating on a 172.17.1.x subnet.
Got it.
And in the middle, sitting between them, you have a Kubernetes cluster running the monitoring stack.
Okay, so the translation from Docker to Kubernetes introduces some abstraction layers that we definitely have to configure. You don't just put a JSON token in a folder on a server anymore.
No, you create a Kubernetes namespace, specifically Weka monitoring, to logically isolate the CPU and memory resources.
And then you ingest that highly sensitive cluster admin token into a Kubernetes secret.
Which is a massive cryptographic upgrade.
Huge. Instead of relying on a fragile Chmod 400 file permission on a single server, the token is now encrypted at rest within the Kubernetes etc. database.
Right. And the orchestrator injects it directly into the pod's memory space only when the pod is actually scheduled onto a worker node.
It is vastly more secure.
Yeah.
But I think the real evolution here is in the config map. In the 4.x Docker setup, the exporter configuration essentially just pointed at the cluster and scraped a broad, predefined set of metrics.
Very generic.
But the 5.1x Kubernetes Weka exporter-config.yaml is a highly granular declarative manifest.
It really is.
I'm looking at the stats block in this config map. It is explicitly declaring the exact telemetry required. It asks for CPU utilization. It asks for OPS, input-output operations per second. It asks for read bytes and write bytes.
But the crucial ones, the metrics that actually matter the most to a storage architect, are read latency and write latency, and those are measured in microseconds.
Why do you say those are the only ones that actually matter?
Well, because throughput and IOPS can lie to you.
Really? How so?
Think about it. If your application team says the system is slow, and you look at your IOPS and see 500,000 operations per second, you might think, wow, the cluster is working incredibly hard, everything is fine.
Right. Big number equals good.
Exactly. But if those 500,000 operations are queuing up and experiencing 2,000 microseconds of write latency, the application is actually choking. Latency is the ultimate arbiter of true storage health.
That makes total sense. In an NVMe and InfiniBand environment, you expect latency in, the low tens of microseconds?
Yes, very low. So spikes into the hundreds or thousands indicate a massive hardware bottleneck or some sort of network fabric degradation.
The fact that the Supermicro Guide forces the administrator to explicitly declare these latency metrics in the config map really shows a deep understanding of what constitutes actionable telemetry.
It's not just gathering data for the sake of data. So we have the config map dictating what to pull. Now we need to deploy the exporter pod to actually pull it.
And this is where the networking complexity of Kubernetes introduces a really fascinating challenge. The guide uses a node port service, mapping external port 15081 to the container's internal port 8001.
Let's break down the mechanics of a node port because it is fundamentally different from Docker's host networking that we were just trashing.
Yes, let's. In Kubernetes, a pod is completely ephemeral. If a worker node crashes, the orchestrator immediately spins up a replacement exporter pod on a completely different node.
And when that happens, the new pod gets a completely new internal IP address.
So if Prometheus was statically configured to scrape a specific pod IP, the pipeline would shatter every single time a pod restarted.
Exactly. The node port solves this by modifying the IPTables or IPVS rules on every single physical worker node in the Kubernetes cluster.
Okay.
When you declare node port 150.0.81, the kube proxy service essentially opens port 150.0.81 on node A, node B, node C, all of them.
So Prometheus can send a request to the physical IP address of any Kubernetes worker node on port 150.0.81. The kernel of that node intercepts the packet, consults its iptable's routing rules, and then seamlessly forwards the packet across the internal overlay network directly to the ephemeral exporter pod.
Regardless of which physical node that pod is currently residing on, it acts as an incredibly robust, dynamic load balancer.
It's brilliant. But while the incoming K8's networking is highly dynamic, the outgoing networking, how the exporter talks to the Weka cluster, presents a massive architectural contradiction in this guide.
Oh, I know exactly what you're about to bring up.
Yes. I found this buried in the Weka exporter-deploy.yaml pod specification. It's a block called hostaliases.
It immediately jumps out at you, doesn't it?
It really does. The guide instructs the administrator to manually map the IP address 172.172.1.93 to the hostname S1, 172.17.1.94 to S2, and so on, hard-coding this directly into the deployment manifest.
Yeah.
It feels like an egregious anti-pattern. The entire philosophy of Kubernetes is dynamic discovery. You don't hard-code IPs, you rely on core DNS.
You're not wrong.
By injecting these hostaliases, we are dragging the brittle, static nightmare of the Docker era right back into our elegant Kubernetes architecture. If the network team re-IPs the Weka cluster, the monitoring pipeline instantly breaks. Why on earth would Supermicro mandate this?
It is a phenomenal catch, but it forces us to talk about the harsh reality of enterprise DNS brittleness. You have to consider the failure domain here.
Okay, lay it out for me.
The Weka exporter is querying the Weka API, right? The API responds with an array of node health data, identifying those nodes by their static host names, S1, S2, S3.
So the exporter parses that payload, sees node S1, and needs to query S1 directly to pull deeper metrics.
Precisely. Now, if you rely on the standard corporate DNS server to resolve S1 to 172.17.1.93, what happens when the corporate Active Directory or bind servers experience an outage?
Ah, I see. The DNS goes down, the exporter suddenly can't resolve S1, and the metrics immediately stop flowing.
And what happens on the SEC dashboard when the metrics stop?
The dashboard goes red, the alarms fire.
Right. It looks like a catastrophic failure of a 100 petabyte storage cluster. But the storage cluster is perfectly fine. The AI training models are still running at Mach 3. You just triggered a massive false positive because your monitoring pipeline relied on an external vulnerable dependency.
Wow. Okay. So by using hostaliases, Kubernetes actually intercepts the DNS request at the pod level. It just modifies the local echosts file inside the exporter container itself.
It short-circuits the DNS lookup entirely. Supermicro is intentionally trading Kubernetes purity for monitoring survivability.
That's fascinating.
You never want your observability stack to be dependent on external infrastructure that is more fragile than the system it is supposed to be monitoring. It is a deliberate, highly engineered compromise.
I should love that. It's the kind of pragmatic engineering decision you really only learn after suffering through a massive outage.
Oh, absolutely.
Okay, so the exporter is resilient at pulling the data. Now we need our time series engine. Section 2 of the 5.x guide walks us through deploying Prometheus onto the K8's cluster.
The networking here is fairly straightforward internal routing. Prometheus uses the service name weka-exporter.weka-monitoring.svc.cluster.local to scrape the data without ever leaving the K8's overlay network.
Nice and clean.
But there is a storage configuration in the Prometheus-weka.yaml file that requires severe scrutiny.
You were talking about the volume section?
Yes.
The guide defines the Prometheus data volume using a configuration that simply says empty dir. I cannot stress this enough for anyone listening who is building out infrastructure.
Right.
This is a massive red flag if taken blindly into production.
We need to dissect the philosophy of Kubernetes storage to understand why. Kubernetes treats storage as entirely distinct from compute. When a pod is scheduled, you have to explicitly tell it where to save its data.
And an empty dir volume is exactly what it sounds like. It just creates an empty directory on the physical disk of the worker node where the pod is currently running.
And the critical flaw is its lifecycle. An empty dir volume exists only as long as that specific pod continues to run on that specific node.
So if the Prometheus pod crashes due to, say, an out-of-memory error,
Or if the orchestrator evicts it to balance the load across the cluster.
right, that pod is destroyed.
Yeah.
And the exact moment the pod is destroyed, the Kubernetes kubelet process permanently deletes the empty dir from the disk.
Poof. Gone. Every single byte of your historical performance data. The latency trends from last week. The IOPS baseline from last month vanishes instantly. Prometheus spins back up on a new node with a completely blank database.
Why would the Supermicro guide use this? Is it just a mistake?
It is not a mistake. It is a context limitation. This is an integration guide meant to validate the pipeline. Empty-dir requires zero storage provisioning overhead.
Oh, edit.
Yeah, you don't have to configure ISCSI targets or map LUNs to your K8s cluster just to prove that SEC can see Weka metrics. It makes the tutorial frictionless for the reader.
But the unwritten assumption is that a senior systems engineer reading this manual knows they absolutely must rip out empty-dir and replace it with a persistent volume claim tied to a highly available SAN before ever going to production.
Exactly. If you want a time series database to actually remember time, it simply cannot rely on ephemeral storage.
Speaking of time, we have to talk about the most insidious requirement in this entire manual. It's tucked away in this small warning block. The SEC appliance, Kubernetes node, Prometheus pod, and Weka cluster should have synchronized system time.
Network Time Protocol, NTP. It sounds so mundane, but clock drift is responsible for some of the most baffling outages in IT history.
I always think of it like a team of detectives trying to build a timeline of a crime, but every single witness has their watch set to a completely different random time zone, and none of them are actually aware of it.
That's a great way to visualize it.
Witness A swears the suspect left at 12:00. Witness B swears they arrived at 11:30. You cannot build an objective reality out of unsynchronized perspectives.
And the mathematical reality of a time series database makes this even more critical. Prometheus doesn't just store logs as text. It stores data points on a strict Cartesian plane where the x-axis is a hyper-precise UNIX timestamp.
Let's walk through the math of a failure here, just to make it concrete. Let's say the Weka cluster's hardware clock drifts 5 minutes into the future because NTP failed silently.
Okay.
The exporter pulls a metric, let's say 500 IOPS, and tags it with Weka's future timestamp.
So Prometheus scrapes that metric, pulls it into its database, and then compares the metric's timestamp against the Prometheus server's local clock.
Right.
Prometheus immediately sees a data point from 5 minutes in the future.
What does the database engine actually do with that?
Best case scenario, it just drops the metric entirely as invalid data. Worst case scenario, the PromQL engine attempts to calculate a rate of change over a time vector, say, rate, we count as 5 meter. If the timestamps are skewed, the denominator in that equation becomes skewed. You end up with mathematically impossible results.
Like the dashboard suddenly reporting negative 50 microseconds of latency.
Yeah.
It's basically telling you the Weka cluster is finishing write operations before the application even initiates them.
Which is exactly why the guide mandates NTP. Every single node in this entire telemetry pipeline, from the bare metal storage nodes to the virtual K8s workers to the SCC appliance itself, must be rigorously syncing their clocks to the same internal Stratum 1 or Stratum 2 time server.
Because if the clocks diverge, the entire mathematical foundation of your observability just collapses.
Hopefully.
Okay. We've secured the cluster admin token. We have debated Kubernetes networking and survived the empty-dir trap. Our clocks are perfectly synced via NTP. We have built a pipeline. We are ready for the final mile. We are ready to log into the SuperCloud Composer dashboard.
This is the fun part. This is where we move from the command line into the visual realm. The guide provides the exact navigation path in the SEC web UI, admin, then external service, then performance metrics, then Prometheus.
And right here is where an administrator could easily stumble based on our earlier architectural discussion. SEC asks for an IP address and a port to connect to the telemetry source.
It is vital to remember the pipeline architecture here. The guide notes explicitly that SCC connects to Prometheus only. It does not know how to talk to the Weka exporter.
So for the IP address, we input the Kubernetes worker node IP, our 172.31.44.116 address. But the port configuration requires us to recall how Kubernetes services route traffic. The internal Prometheus container operates on port 9090. If an administrator types 9090 into the SEC interface, what actually happens?
The connection just times out.
Really?
Yeah, the Kubernetes host firewall will drop the packets. Unless the SEC appliance is deployed inside the exact same Kubernetes overlay network, which is highly, highly improbable, it cannot route to the internal container port.
You have to use the node port mapping. The guide configures the Prometheus service to map internal port 9090 to external node port 15090.
So you must enter 5090 in SEC. You are essentially knocking on the external door of the Kubernetes cluster, asking the kube proxy to route you internally to the Prometheus database.
We input the node port, we hit save, and the connection establishes. We navigate to the Storage Metrics tab. Let's paint a picture of what this unified dashboard actually looks like based on the source images in the manual.
The interface is a highly refined widget-based layout. It completely abstracts away all the JSON and YAML we just spent hours configuring. In the top left, you have the immediate Boolean indicators, like cluster status, which will hopefully render as a nice green good.
Beside that is the architecture widget. It explicitly identifies if the Weka cluster is running over Ethernet or InfiniBand. I actually find it fascinating that this specific detail warrants top-tier placement on a visual dashboard.
Well, it warrants that placement because it fundamentally dictates your performance baseline. InfiniBand utilizes RDMA, remote direct memory access.
Meaning the network interface cards can transfer data directly from the memory of one server to the memory of another server, completely bypassing the CPU and the operating system kernel on both sides.
Exactly. It provides near zero latency. Standard Ethernet historically relies on the TCP/IP stack, which requires CPU interrupts and buffer copying, introducing massive latency by comparison.
So it's a huge difference.
Oh, massive. If a storage architect logs into SCC and sees Ethernet on a cluster they specifically designed for InfiniBand, they instantly know that a catastrophic fabric failure has occurred, and the system has fallen back to a slower protocol.
It's a brilliant early warning indicator. Moving across the dashboard, we hit the capacity metrics. You see cluster size, indicating the number of physical nodes, alongside total size and unprovisioned size.
And right below that is the protection status's pie chart. This is the visual representation of Weka's self-healing capabilities.
In a healthy system, it's just a solid green circle indicating severe failures. But at petabyte scale, hardware failure isn't a possibility. It's a statistical certainty. NVMe drives will die.
They absolutely will. And when a drive dies, Weka immediately begins rebuilding the lost data blocks using parity data scattered across the surviving drives.
It just heals itself.
Yes. And during that rebuild phase, a sliver of the SEC pie chart changes color to indicate one failure.
The storage is still online. The application team doesn't notice a thing, but the operations team sees the visual indicator on the dashboard. They can dispatch a data center technician to swap the physical NVMe drive without ever having to SSH into a command line interface to parse cluster health logs.
And that is the operational ROI of this entire complex pipeline. You unify the hardware lifecycle management of the Supermicro servers with the software telemetry of the Weka file system into a single pane of glass. It drastically reduces the cognitive load during an incident response.
But as we know all too well, the pipeline itself can break. And staring at a blank dashboard while an incident is occurring is terrifying. Which brings us to the final and, frankly, most crucial section of the 5.x manual, the troubleshooting methodology.
Supermicro doesn't just provide a list of disparate commands here. They enforce a strict bottom-up diagnostic philosophy. When the dashboard goes dark, you do not start by clicking randomly in the SEC UI.
No, you have to trace the plumbing from the source.
You isolate the network hops. Layer 1 is the exporter, Layer 2 is Prometheus, Layer 3 is SEC.
Let's start at layer 1. The dashboard is blank. Your first hypothesis should be the exporter pod is dead. You drop into the Kubernetes command line and run kubectl /zen Weka monitoring, get podio wide.
You are checking the lifecycle state. Is it in a crash loop backoff? Did the kubelet fail to pull the container image? If the pod isn't in a running state, you use kubectl describe pod to read the kernel events.
But let's assume the pod is running perfectly. Layer 1 seems healthy, but metrics still aren't flowing. The guide instructs you to investigate the authentication token.
If the cluster admin token was typed incorrectly into the Kubernetes secret, or if someone rotated the credentials on the Weka side, the exporter pod will run fine, but every API call it makes to Weka will be rejected with an HTTP 401 unauthorized error.
The isolation technique here is to check the container logs using kubectl logs. If you see authentication errors, the guide dictates remediation. Regenerate the token on Weka, delete the K8 secret, recreate it, and restart the pod.
Straightforward enough.
Okay, but my instinct here is to say, what if the token is perfect, the pod is running, and there are no auth errors in the logs, but it still isn't working? We talked about DNS brittleness earlier with the host aliases. How do you definitively prove that the exporter can actually route traffic to the Weka physical nodes?
You have to test from the inside out. You cannot use ping from your laptop. You have to step inside the container's network namespace. The guide relies on kubectl exec deploy Weka exporter get in host S1.
This is a brilliant command. Kubectl exec forces the command to run inside the running exporter pod. It asks the pod's internal OS to resolve the hostname S1.
If the command returns the IP address 172.17.1.93, your hot aliases configuration is flawless. If it returns nothing or a timeout, you have isolated the problem. Your K8's deployment manifest has a typo, and the exporter is literally blind to the storage cluster.
Okay, let's assume layer 1 is completely validated. The exporter sees the cluster, the auth is good. We move up the pipeline to layer 2. Prometheus.
If Prometheus isn't pulling data, the most common culprit is a failed scrape target. The guide provides an excellent command to interrogate the internal Prometheus API, curl nashes http://172.31.44.15090 ham a1 targets JQ.
Piping that output into JKey is so critical because the raw API response is a massive, unreadable wall of JSON.
Oh, it's impossible to read.
Yeah. JKey parses it into a clean, human-readable format. You're looking for the health status of the wiki job.
If the health status is down and the last error says connection refused, you have an internal Kubernetes networking failure. Prometheus cannot reach the exporter.
Again, testing from the inside out. I would use kubectl-exec to drop into the Prometheus pod and try to reget or curl the internal ksdns name of the exporter. Weka exporter is at weka-monitoring.svc.cluster.local.8001.
Exactly. If that internal curl command succeeds but the Prometheus target still says down, you know the network is fine and you likely just have a typo in your prometheus.email scrape configuration.
You isolate the variables, proving what works to isolate what doesn't. So layer 1 is perfect, layer 2 is perfect. Prometheus targets show UP. You can query the database directly and see the metrics. The filing cabinet is full.
Right.
But layer 3, SEC, is still throwing an error. External Prometheus service not configured.
If Prometheus possesses the data but SEC cannot display it, you have perfectly isolated the failure domain. It is absolutely not a Weka hardware issue. It is not an exporter software issue. It is strictly a network bridge issue between the SEC appliance and the Kubernetes node port.
You check the SCC configuration. Did you mistakenly use internal port 9090 instead of external node port 15090? Is the enterprise firewall blocking SEC's IP address from hitting the Kubernetes subnet?
Or, returning to our time travel paradox, are the clocks out of sync?
Yes.
If SEC requests data for the last 15 minutes, but its internal clock is an hour ahead of the Prometheus server, Prometheus will dutifully return an empty graph.
It fundamentally always comes back to NTP, DNS, or firewall ports, doesn't it?
It really does.
But by employing this strict layered troubleshooting methodology, you transform a massive, terrifying IT outage into a solvable logic puzzle. You aren't guessing. You're systematically proving the integrity of each link in the chain.
Which is exactly what you need when the pressure is on.
We have covered an immense amount of architectural ground today. We started by exploring the sheer power of a parallel Weka cluster, bypassing the kernel to push NVMe to its limits. We analyzed the early 4.x era, debating the security of cluster admin tokens locked down with SHA-400 400 and the monolithic dangers of Docker's network mode.
Then we tracked the evolutionary leap into Kubernetes in the 5.x era. We dissected granular config maps, the Iptable's magic of node ports, and the pragmatic compromise of hard-coding host aliases to survive enterprise DNS outages.
We narrowly avoided the catastrophic data loss of the empty dir trap, unraveled the mathematics of time series databases to understand why NTP is so critical, and finally, we illuminated the unified SuperCloud Composer dashboard, translating raw latency metrics into actionable hardware intelligence.
The journey from the noisy, high-frequency trading floor of the Weka cluster to the quiet, analytical dashboard of SCC is highly complex, but it is deeply logical. Understanding the why behind these configurations is what separates a technician who just copies commands from an architect who can design and rescue enterprise systems.
I want to leave you with a final thought that extends beyond the manuals we've read today. We've spent this entire deep dive analyzing how to build a complex, multi-layered telemetry pipeline specifically for human eyes.
Right.
We extract the data, we translate it, we store it in Prometheus, all so that SuperCloud Composer can draw beautiful pie charts for a human administrator to look at and make a decision about replacing a drive or investigating a latency spike. The dashboard is the ultimate human interface.
It relies entirely on human interpretation and human reaction time.
But as machine learning models begin to ingest Prometheus time series data directly natively, understanding the multi-dimensional math of PromQL without needing a visual chart, how long until the storage cluster starts dynamically re-architecting itself based on its own telemetry?
Oh, that's a fascinating thought.
How long until Weka detects a microsecond latency spike on an InfiniBand port, automatically queries Prometheus for historical context, realizes a switch is degrading, and instantly reroutes its own RDMA traffic without a human ever knowing it happened?
A fully autonomous, self-healing data center.
Exactly. If the machine becomes its own conscious brain, capable of interpreting its own nervous system telemetry, how long until we effectively remove the human administrator and the dashboard entirely from the loop? Will we go back to not needing to read the telemetry because the infrastructure is finally capable of healing itself? Something to mull over. Until next time.